right, well, hello, Honors Algebra 2. This is the third and possibly final lesson for this unit, depending on how far you want to take your studies. The reason I mentioned that, let me go back to the summary page for this unit. If you did not get a chance to look at kind of the summary, 10.4 is an optional section. What that means is that I'm still going to post a video for it. I'm still going to post homework for it. I'm still going to post extra practice for it, but it will not be on your quiz on Friday. That being said, it is going to be something that's covered next year in either Honors Pre-Calc or College Algebra Trig. So if you want to make sure that you know those things for next year, then I would highly recommend going through 10.4. Okay. So for today, what we are going to focus on is we're going to look at our third trig ratio, which was tangent, and talk about how its graph is. In addition to that, we're also going to talk about some applications. So we're going to talk about where some of these curves get used in the real world. But let's start with tangent, kind of looking at what it is and how it behaves. And let's start by kind of taking it in the same way we did sine and cosine. So if you have not already, I would recommend pausing the video and finding either your notes for where you filled in this table for sine and cosine, or go ahead and copy in these values real quick. In fact, I just went ahead and copied and pasted them straight into this section of the notes. So if you need to, take a minute, pause the video, make sure you've got all these values, because we're going to be using them to find tangent. Okay, so for tangent, if you recall, tangent was the same as taking y over x or as taking sine over cosine. And so the table actually works out pretty conveniently because it already has sine over cosine. So if you think about it, for this first one, you're taking 0 divided by 1, which is 0. For the next one, 1/2 divided by the square root of 3 over 2 would be the same as multiplying by the reciprocal. And I'm sure you remember doing this when we were evaluating tangent. You get 1 over the square root of 3, which eventually, when you rationalize, becomes square root of 3 over 3. This is also where it's a really good time, if you hadn't already, to have all of those kind of convenient values for tangent filled in. So if you've not already filled in tangent on your unit circle, I would highly recommend going around and doing that at some point. For the next one, pi over 4. We're going to take square root of 2 over 2 divided by square root of 2 over 2, which just ends up being 1. And then I'm not going to show the steps for it, but if you take square root of 3 over 2 divided by 1 over 2, you just get square root of 3. And then what's kind of interesting is when you get to pi over 2. When you take 1 and divide by 0, it's not 0. I'm hoping that at this point in the year especially, that we've all come to understand that dividing by 0 is not 0. 0 divided by a number is 0, but a number divided by 0 is undefined. So what that's going to do is that's actually going to show up in the form of an asymptote. And I think we've seen these in quite a few units this year. Rationals, we saw them. Exponential and logarithmics, we saw them. We also are going to have some asymptotes in this unit as well. But then from there, we can kind of evaluate the rest of these pretty quickly. Just they're going to be the same values, but with a negative maybe in front instead. So here would be -1, negative radical 3 over 3, and then 0 divided by -1 is 0. And as we keep going around, here's square root of 3 over 3, and then this would be 1, positive square root of 3, and then divided by 0 again is undefined. And as we continue around, negative square root of 3, -1, negative square root of 3 over 3, and 0. So again, I'm kind of going through those a little bit more quickly. If you need to go through and show the steps for dividing, I get that. Just pause the video before you go on to the next part. But what you're going to find, even just looking at the table, is that tangent repeats more frequently. And that was something we talked about when we were solving trig functions as well. If you notice, the values for tangent actually start to repeat after just pi radians. For sine and cosine, it took us a full 2 pi radians. In other words, one whole trip around the unit circle before we started to repeat. Notice for tangent, it only takes a half a trip around the circle, or pi radians, to get there. So that's an important thing to remember, is that tangent repeats more frequently. And again, based on what we did last unit, hopefully that's something you're pretty familiar with. Okay, so in putting this on our graph, while we could sit here and go through and graph every single point possible, I think it'll be easier if we just focus on the points that we focused on last time, which are any of those points end up being kind of a whole number or an asymptote. I think those are going to be equally important points for us to put on our graph. So we're not even going to put all these points on the graph. We're just going to focus on the ones I highlighted. So we're going to go through about every other point to put on our graph here. So graphing these, our first one we had was at 0 and 0, so we're going to have a point right here. And then at pi over 4, which will be halfway in between, we're at a y value of 1. I'm going to count by half numbers this time, so I'm going to put 1 right here. And then at pi over 2, we are undefined. We mentioned that that's going to then be an asymptote, so I'm going to draw that in as so. At 3 pi over 4, which would be halfway between 0 or pi over 2 and pi, we're now at -1, so that would be right here. And then at pi, we're at 0. And at 5 pi over 4, we are at +1. And then at 3 pi over 2, let me get that other point in the right spot. There we go. At 3 pi over 2, we are undefined. That's our next asymptote. And then at 7 pi over 4, so halfway in between here, we're now back at -1. And then at 2 pi, we're at 0. Now, you probably are not going to be able to see the shape based on those points, so I'm going to kind of help you with that. If you wanted to, you could always find kind of the decimals for these or use a graphing calculator. What you're going to find is that tangent curve kind of does this kind of zigzag, and it approaches the asymptotes in either direction. It's almost kind of cubic in a way. It's kind of a good comparison to make for it. It's almost like a cubic graph that continues to repeat. So you've got this graph, and I've shown you there kind of three different sections of the graph, where this graph obviously is going to continue to repeat. But that at least gets you kind of the idea of what it looks like. So let's talk about some of the key characteristics that we might notice. For the domain, notice that the domain is, for the most part, all real numbers. And I'm going to write it this way. This is all real numbers except for where we have our asymptotes. And if you didn't already kind of pick up on the pattern, you've got pi over 2, 3 pi over 2. The next asymptote would have been at 5 pi over 2. In other words, the odd multiples of pi over 2. So everywhere except for those odd multiples, so 1, 3, 5, 7, 9, or even going back to the left, negative pi, -3 pi, -5 pi over 2, all those values as well. Notice that the range isn't restricted at all. Notice that you're continuing down forever as well as up forever. So your range there is going to be negative to positive infinity. Or again, if you wanted to just use that set notation of all real numbers, that would work as well. The next thing to point out is the x-intercept. So this is a little bit different, not necessarily something we talked as closely about with sine and cosine, but x-intercepts are kind of a critical point. We don't really have a midline. We really don't have an amplitude when we talk about tangent. So these are kind of the other key parts that we use to help us kind of graph. So the x-intercepts, if you notice, happen every pi. So 0 pi, 2 pi, 3 pi. And again, I've got the plus and minus. That way, if you wanted to go kind of in this negative direction, you could go to the left as well. For asymptotes, we've already kind of talked about those. That's kind of the same as what it was for our domain. So those odd multiples of pi over 2. Notice that I've included the absolute value of b in the denominator. That way, it doesn't just work for the parent function, but as long as we divide by that absolute value b, it works for any function, any transformation of tangent itself as well. And then for period, a similar formula that we had, if you remember, our period formula for sine and cosine was to take 2 pi divided by b. Now that formula for period is to take just 1 pi divided by the absolute value of b. So a similar formula, but notice that the period is a little bit more frequent here when we talk about tangent. So to give us some practice, we're now going to graph our function of g of x equals 2 multiplied by the tangent of 3x. So probably the easiest thing to do first is to figure out where your asymptotes are going to be. So if we think about where our asymptotes are going to be, we've got that formula for that, which is going to be to take pi and divide by 2 multiplied by our b value. In this case, that was 3. So that tells us that we're going to put asymptotes at every odd multiple of pi over 6. So if you think about the way this has been divided, pi over 2 means that each of these grid lines is conveniently pi over 6 for you. So this is 1 pi over 6. This is 3 pi over 6. This is 5 pi over 6, and so on. So it's kind of a nicely labeled graph for us to add in all of these odd multiples of pi over 6. So next would probably be to find our x-intercepts. And really, it's probably easiest to think about the x-intercepts by the fact that they are halfway between the asymptotes. I'm just going to add that up here. Halfway in between our asymptotes is where you're going to find your x-intercept. So there's going to be an x-intercept here, 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 and here. Now, obviously, if we had had some kind of a transformation like a +2 or something like that, then all those x-intercepts then get moved up by 2. That's really the only thing you have to worry about. We didn't have to worry about that in this case. Last is going to be that 2 that's in front of our tangent. What that helps you to decide is how far you go up or down in between your x-intercept and your asymptote. To give you an example, here, the number in front of tangent was a 1. That meant that if you went halfway between your x-intercept and your asymptote, then you were going to either go down by 1 or you were going to go up by 1. So kind of similar to an amplitude, I suppose, but not quite the same thing. So if I make this -1, make this +1 to make it consistent, then halfway in between this x-intercept and its asymptote here, we're going to put a point. And then we'll just continue to do that. So halfway in between x-intercept and asymptote, we'll continue to move a point either down by 1 or up by 1. And then we'll go back and draw in each of these pieces of our tangent curve. So tangent, you can draw quite a few of those periods. The first one here kind of gets split in half, but then starting on the next one, you can draw in a full cycle of tangent, or a full period of tangent, depending on how you want to think of it. And then that repeats and continues to repeat, and eventually we'll get all the way through this here. Finally. Okay. Cool. So that pretty much takes care of tangent. So the other part that I wanted to talk about in the notes today was some of the applications that we have for our sine, cosine, and tangent curves. Before we can really dive fully into these, there's a definition that I need to give to you, which is this idea of frequency. So frequency is the number of cycles per unit of time. Another way to think about it is as the reciprocal of the period. In other words, your period is equal to 1 over your frequency, and frequency is equal to 1 over your period. So a couple different formulas that can be useful depending on what you're looking at. Okay, so in this example that we're going to look at, a sound consisting of a single frequency is called a pure tone. An audiometer produces pure tones to test a person's auditory functions. An audiometer produces a pure tone with a frequency f of 2000 hertz, which are cycles per second. The maximum pressure P produced from the pure tone is 2 millipascals. Write and graph a sine model that gives pressure P as a function of the time T in seconds. Now, here's what I want to kind of level with you guys. I don't know anything really much about audiometers and how they work. But here's kind of the cool part, is if you understand the math behind it, you really don't have to understand how an audiometer works to be able to work through this problem. So let's kind of find some of the key features to first write our equation, and then we'll work on our graph second. So writing our equation, let's kind of think about some of the key pieces that we already know. The first is that we've actually been told what type of equation we're going to use. It's telling us already that we're going to use a sine model. Another thing that's kind of helpful is it tells us the maximum pressure is 2 millipascals. So already, if you want to think about maximum, that's your amplitude. So we already know our amplitude is going to be a 2. Okay. We weren't really told that it's been shifted up or down, so we probably don't have to worry about a midline. So midline, we can probably just assume is through y equals 0. The only thing we have left to find is our period. And really, we know what our period is, which is that there were 2,000 hertz per second. So there's our period. Well, actually, I take that back. That's not really our period, is it? That's our frequency. So let's maybe take a step back. It didn't tell us period. I misread. That was frequency. So we've got a frequency of 2,000 hertz. Okay. So let's plug that into this equation on the right here. I think that one might be a little bit more useful. So if I plug in 2,000 for f, it's equal to 1 divided by our period. And remember, for a sine model, period is 2 pi over b. And then remember that if you are wanting to divide by a fraction, that's the same as multiplying by the reciprocal. So that would be the same as b over 2 pi. Okay, so rewriting that equation, let's see where that gets us. We've got that 2,000 is equal to b over 2 pi. The only thing we have left to do is solve for b. So let's multiply by 2 pi on each side. And it looks like our b value is going to be equal to 4,000 pi. Okay, so let's write our equation. We want it as a function p, so we're going to say p is equal to our amplitude, which is 2, multiplied by the sine of our b value, which was 4,000 pi, multiplied by, we wanted it in terms of the time t, and again, we did not have an amplitude, so we're going to not have to put the plus 0. Okay, that actually should make it a little bit easier to graph now. So we're thinking about kind of how that's going to work. We never did actually directly find our period. Let's go ahead and find that now. So our period, remember, was 2 pi divided by b, and b we found was 4,000 pi. So once we've simplified, pi divided by pi is 1, and then 2 divided by 4,000 is 1 over 2,000. That's going to be helpful in kind of labeling our graph here. So our period, we're going to go from 0 up to 1 over 2,000. So then if you think about what half of that would be 1 over 4,000. And then half of 1 over 4,000 would be 1 over 8,000. And so on. And then let's see, our amplitude was 2, so we'll go up by 2. Or well, up by 2, and then down by 2. Midline was at 0, so if you're wanting to fill that in, kind of like an asymptote, there you go. And then for sine, we've got our first point on our x-axis, up by an amplitude, back down by an amplitude, down by another amplitude, and back up. And once we connect our dots here, we should be good to go. So here would be a model for what that sine wave would look like. So this would be a model for a pure tone based on the labels that we've got. And I guess if you want to label the variables, you've got t here, you've got p here. Okay, let's take a look at one more example of kind of where these can show up in the real world before we're done with this lesson. So in this last example, we've got 2 people that are going to swing jump ropes. So double Dutch maybe is how you've heard this, that's shown in this diagram. It tells us the highest point of the middle of each rope is going to be 75 inches above the ground, and the lowest point is 3 inches above the ground. The rope makes 2 revolutions per second. We're going to write a model for the height h in inches of a rope as a function of time t in seconds, given that the rope is at its lowest point when the time t is equal to 0. Okay, so let's do a couple things. Let's maybe try to find either amplitude or midline. Let's maybe do midline first. So our midline. you could put these on a graph if you wanted to. This is probably where it's easier to think about finding the average between those two values. So if you take your maximum, which is 75, plus your minimum, which was 3, and divide by 2, that will simplify to be 39. So 39 inches would have been our midline for this equation. So then amplitude, you're looking at what is the distance from that midline either to your maximum or minimum. Let's just go distance to the minimum. So 39 minus 3, the difference there is 36 inches. So then there's going to be your amplitude. The only thing we have left to find is going to be our B value. So it tells us that it makes 2 revolutions per second. So if it's rotating at 2 revolutions per second, the period 2 pi over b is going to be equal to 0.5. Because if you think about 2 revolutions per second, the time it takes for 1 revolution is going to be just a half a second. In other words, your period is 0.5. So to get your b value, you're going to have to work backwards for that. You're going to have to solve for b, just swap it with the other side. So take 2 pi divided by 0.5, and that should get you your b value, which is going to end up being a b value of 4 pi. All right. The only last thing we have left to do is it says that the rope is at its lowest point at time 0. So if you think about just kind of what that graph would look like, and this is just a sketch of it, we're not going to actually graph it, but just to decide what it's going to look like, is that if our rope starts at its lowest point at time 0, so I guess it would start at 3 inches at time 0, then it would go up to its 75 inches, and then back down to 3 inches. So if you think about what that's going to be between sine and cosine, because this time it didn't tell us which one to use, to me that looks like it's going to make a little bit more sense to be a cosine curve. So as we fill in our equation, let's go ahead and do that now. Let's just call it, let's say they wanted it as a height h, so we'll say h of t for our function is equal to our amplitude, which was 36, multiplied by the cosine of b multiplied by x, so 4 pi, well I guess not x, but t, plus our midline, which was 39. Now here's the only part that's kind of tricky, is that since you're not starting up at an amplitude, you're starting down at an amplitude. If you think about what's happened to your cosine curve, it's been reflected over that midline. That means that you have to put a negative in front of that amplitude. So it's actually going to be a negative 36 cosine of 4 pi t plus 39 for our final answer. And again, this one didn't ask us to graph it, so we're not going to bother with that with this one. I will just say, guys, on your homework for this section, there are two application problems on it. If you follow what we did in the notes, those 2 problems shouldn't be too bad. So please make sure you've followed along. Make sure that you've worked through these example problems so that you can understand what you're doing on big ideas for the homework. That being said, if that's all you kind of cared to learn for this unit, that's all that's going to be on the quiz this Friday. I will just say, though, that I'm going to try to go pretty quickly through graphing cosecant, secant, and cotangent, all of which are going to be things that you'll see next year. And if you want to have kind of a head start and a good foundation for next year, I would highly recommend taking the 20 minutes to watch that video whenever you can. That being said, guys, have a good rest of your day. I'll talk to you next time.